Hello! Let's go through a submerged surface problem. And what this is a distributed load problem. So if you can get really good at the distributed loads, all you're doing is the same thing as what's on this beam over here. We've just rotated it. And for water, we can figure out what this load is based on the water pressure. So rho GH, the density of water times gravity times height. The deeper you go, the more pressure there is. Okay, so let's just go through one of these distributed load problems one more time really quickly so you remember what it is. And then we're going to take it and turn it on its side and turn it into a submerged surface problem. Here's just another quick distributed load problem. What we're going to do, determine the distributed load W naught over here, at the end A of the beam, ABC, for which the reaction at C, here's in C, the reaction at C is 0. And we're also going to find the corresponding reaction at B. Okay, if we drew a free body diagram of this guy, we would have B here in the middle, and then it's going to be balanced so that nothing is happening at C. So this distributed load, what we can do is break it up into this green triangle over here. So it's going to have a center of mass, 1/3 from the base, and then we have a blue triangle over here, and it has a center of mass, and there's its base. And those two guys are going to act like the two sides on a teeter-totter. Okay, so we have the green side over here, and we've got the blue side over here. And B is in the middle, and then C, we're going to pretend like C isn't even there, so it's not holding it up. So the green and the blue triangle are just going to balance each other. So we're going to figure out what these two reactions are and just kind of balance those out. So here's working through the math of that. For triangles, the center of mass of a triangle is 1/3 up from the base. 7 plus 5 is 12, 4, 8, 12. So we're going 4 over for where the weight of the green chunk is acting and 4 over for where the weight of the blue chunk is acting. We also need to find the areas under the load curve. So the area of a triangle is just 1/2 base times height. In this case, the base is 12. Okay, so here's 12. There's the base. And then the height over here for the green triangle, that is what we're solving for. So that's the distributed load. It's going to have units pounds per foot. So when we multiply pounds per foot times foot, this is going to turn into a force. So we have the green reaction, we have the blue reaction. This guy is just 1/2 base times height 2, 1/2 base is 12, height is 300. There's 1/2 300 times 12. So the blue one is 1800, and what we can do is just take the moment around B. And if you look at the distances, if it's 4 from here, 4 and 5, so it's just 1 over. So 1 times 6W, that's on this left-hand side, and that's going to have to equal, so if it's 4 over 3 plus 4 is 7, so 3. We're going to have 3 times 1800 on the other side. So it's just a little teeter-totter around B. And you can solve for what that distributed load would be, plug that in, find what the reaction would be, and then if we add together both of these guys, that will be what B is supporting. So here's the rest of it. So we have, here's R1, here's R2, we add R1 and R2 together. There's our reaction at B, and here's what that distributed load would be. So it would be 900 pounds per foot on this side and only 300 pounds per foot on that side. So for these distributed load problems, just look at the units. It's some kind of force over some kind of length. Now let's change this over into water. Okay, so let's pretend like this distributed load on the surface is created by water. And we're going to have, again, some kind of a force over some kind of a length. Here's water. So the pressure in water varies with height. So you have the density of the liquid, maybe it's salt water, maybe over in the Dead Sea, or maybe it's fresh water, and you have slightly different densities, gravity, and the height. So as you get deeper and deeper, the pressure gets larger and larger. One thing to remember about pressure is it acts the same in every direction. Okay, so like if you look at a bubble, the bubble is pushed smaller in every direction. It stays circular. It's not going to get flat. So it doesn't matter if you're pushing to the right against a wall, or if you're pushing straight down on the ground, or if you have a wall at some angle. The magnitude of the pressure is rho GH. The direction of it is any direction you want it to be. And usually you just draw the direction of it to be normal to the surface that you are calculating the forces on. So again, it's just a rotated distributed load problem, just like the other distributed loads you've done. Units. If you ever get confused about what's going on, look at the units. It's not just a unit analysis. The unit is the physical quantity that you're trying to relate. The units are the entire point of the whole problem. That's what we're trying to measure and relate. Okay, so force is MA, mass times acceleration. What's mass? How do we get mass? Usually you have some kind of a density. Units on density are kilograms per meter cubed. And if you want to get kilograms out of that, of course, you just multiply it by a volume. For volume, that would be height times area. So put it in terms of height, and this is where that rho GH is going to come out of. Pressure. Usually water, you talk about things like water pressure. Pressure is a force over an area. So multiply force over an area times an area, and you will get a force out of it. Okay, so if we have force over area, and that's mass times gravity over area, you can plug in what mass is, right? So mass is density rho GH times area. Areas cancel out, or pressure is rho GH. Okay, density of water, 1,000 kilograms per meter cubed. So here we go. Pressure is force per area. And if you want to change this distributed load into a single force at a single point, so this is concentrated load versus distributed load. And usually when you solve a problem, you simplify it into just a single concentrated force. So what you're going to do is just take that pressure and multiply it by the area that it's acting over. So you take your force over area times your area, and you get a concentrated load, and that concentrated load acts at the center of mass. Here's a gate. So we have a 0.5 by 0.8 meter gate located at the bottom of a tank filled with water. The gate is hinged along the top edge, A, and rests on a frictionless stop at B. Find the reactions at A and B. How would you go about doing this? What does the distributed load look like? So here we go. We've got pressure. What's the pressure at the bottom? Well, the height at the bottom, that's 0.45 plus 0.48. So down here, we have a larger pressure, and you can plug in density of water is 1,000 kilograms per meter cubed, gravity 9.81, and then here's our height. So rho GH, and we have the pressure acting at this point down here. Next up, the pressure at A. So this one is a little bit shallower, right? It's a little bit smaller. Same thing, rho GH, 1,000 kilograms times G, only now we're only 0.45 meters down, so we have a smaller pressure acting over there. Let's draw those pressures in the normal direction. Remember, pressure acts the same. It doesn't matter which direction it's going to go, so let's put everything in the normal direction. And let's draw the distributed load curve on here. So what we have at the top is a smaller pressure. What we have at the bottom is a larger pressure. And there is our distributed load on the gate. can we change this into two forces and draw a free body diagram of the thing and find the reactions at A and at the bottom? So plug in what we found for the pressures. And here we go. Let's use the triangle method again. So we're going to take this distributed load, break it apart into two triangles, find the area of each triangle. So the one on the top, we can call that P1, and it's just a triangle, 1/2 base times height. We have the size of that gate. It's a 0.5 by 0.8 meter gate. And this guy, if you look at the 0.48 and 0.64 and do a squared plus b squared, this is the 0.8 meter side of it. And then to get the total area, that's going to be the 0.5 piece of it. So it's going back into the board. Okay, so here's our area, 1/2 base, and here's the total area of it, and this is going to turn it into, instead of a load curve, newtons per meter, multiplying it by the depth here, that's going to get out just a straight force. So we have the cross-sectional area of that gate, and we have that pressure that's acting on there, and the 1/2 is because we're looking at a triangle. So it's just 1/2 base times height. And here is the reaction over here for this other triangle. So we have a different pressure at the base. And again, it's a triangle, so 1/2 base times height. If we change these distributed loads into concentrated loads, here's what our free body diagram is starting to look like. And remember, for a triangle, these are going to be located at 1/3 up from the base and 1/3 over. If you feel more comfortable looking at the thing in the same orientation that we did before versus sideways, it's the same kind of force balance, okay? So whether you turn the thing sideways or keep it straight up and down, the easiest thing to do for these problems, orient your coordinate system with as many forces as you can, right? You don't have to break everything into x and y components if you just orient your coordinate system with the gate. So this way, everything is in the y direction. We don't have to worry about anything in the x direction. And then you simply pick a point to take the moment around. So where should we take the moment around? We could take the moment around B, or we could take the moment around A. Let's take the moment around A. And for this case, we just have to figure out how far over each of those forces are. And in our moment equation, we only have one unknown if we're looking at these moments around A. Okay, so this one, it's the force at B versus the weight of the water. And those two forces are going to be acting at 1/3 and 2/3 down. Okay, so 1/3 and then 2/3 over, and you can solve for B. So here's B. And to get A, you can we could take the moment around B, or just add all the forces together in the y direction. Make sure those are 0. And these guys are going to be normal to the gate, so you can figure out what that angle was going to be to measure it. Okay, hopefully that helped you guys. Let me know if you need another video. Try out those Texas Tech videos too. They're pretty good. We'll see you next time.